Hello everyone. So in this lesson, we are going to be studying exponential functions. Now, exponential functions play a major role in our lives. In so many endeavors, we do use exponential functions. Usually, when you go to the bank for a loan, the interest is set up with exponential functions. So we do use exponential functions a lot with retirement, uh, inflation, and what have you. And as we go through these problems, you're going to understand that, exponential functions are very close to us than you can or you have imagined. So, these are the four sections we're going to be looking at. We are first of all going to start with linear versus exponential, and then we'll look at the characteristics of exponential functions, and then we'll talk about using or solving exponential equations by graphing, that is using the calculator, and then we'll talk about uh, applications. All right, so let's begin. Now, in problem 1 in your workbook, we have this problem. Two investments, investment A and investment B. Now, investment A says that you start with $1 and then it's going to double each month. It's going to double each month. Now, we want to make sure that we have the right amount after 12 months. Now, investment B starts with $500 and is going to accrue an additional $100 each month. So A, you're starting with $1, is going to double each month for the next 12 months. And then for B, you start with 500 and each month you get a $100 increase. Which one are you going to choose? So as you think about this, for these kind of situations, especially as we start, you have to analyze the situations, both situations or both investments carefully. So for investment B, you start with 500 and each month is going to increase. So you're going to have 700, 800, 900, 1,000, 1,200, 1,300, 1,400, 1,500, 1,600, 1,700. So that's what we have. Now, what about investment A? So it's doubling every month. It's doubling every month. So all I'm doing is multiply by 2 every time. Wow. So at the end of 12 months, investment A is 4,096. Investment B is 1,700. So definitely A is going to be a better option or a better choice in this situation. Now, when you go to the questions, question A says, write the equation of the function that represents investment A. That is A of t, as a function of time where t is in months. Is this function linear or not linear? So how do we set up an equation or a function for investment A? So I have A of t. Now the thing with what we did was that you know that each month the amount is going to double. So the doubling amount here, and then you put a t on. Remember the t is the input, right? Is this linear? No, it's non-linear. Why is it non-linear? Because the output does not change by the same amount. Remember that for a linear function, the output changes by the same amount every time. But here, that is not what is happening. It keeps doubling instead, okay? So explain your reason. The output does not change by the same amount. That is, the average rate of change is not constant. The average rate of change is not constant. All right, what about B? Write a function that represents investment B, B of t. Now for B of t, if you remember, we started with 500, and then each month is going to increase by $100. And this is linear, right? Why? Because the average rate of change is constant, right? 100 every time. And remember, that is the slope, right? The average rate of change is constant. Is constant. What is the amount of money after 24 months for each investment? So for A of t, you're going to have A of 24 equals 2 to the power 24. And that's going to be a huge sum of money. You have 16 million. If you put this in a calculator. Now for B of t, after 24 months or 2 years, you're going to have 500 plus 1,100 times 24. So this gives you 2,400 plus 500. And that, if you put this in the calculator, you get $2,900. Wow. So look at the difference. Just look at the difference. 16 million. Wow. If I get that money, oh, wow. I'm good to go. I'm good to go. 16 million. Wow. All right. Now we are supposed to draw the graph. So if I label this, let's do that. Oops. So this is going to be my y-axis. Oops, oops, oops. And then that is going to be my x-axis. Now for investment A, remember it's doubling, right? So start from here, and then you go there. I'm going to say this is steps, this is 10. And you're going to have something like that. Yeah, it's not accurate. It's not accurate. If it's accurate, it would have been better. So it's not accurate. Here I have my x-axis and then my y-axis. It's so difficult to draw a straight line on this thing because you're using your finger and then all that, or you're using the mouse. Now here, if this is 250, this is 500. So that is the starting point, right? Then it keeps increasing. 600. Let's do something like that. Uh-huh. 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 You're going to get a straight line. Remember, this is linear, right? So you're going to get a straight line. And that's it. So try to get an accurate graph. Take your time and then draw the graph. Now, let's keep going. What about domain of A of t? Remember that the question says from D, drawing the graph, it says plot A of t and B of t for time up to including 5 months, right? So based on your graphs above, remember we have 5 months. So the domain for A of t for 5 months, you're going to have that. And then you have the same thing here. And then for range, now you go back to the table up there. We started with $1 A of t. And then at 5 months, you have $32, right? And then here, you're going to have 500 for the start. And then you have 1,000, right? Because after 5 months, it's going to be an additional $500. So that's it. All right. All right. Now let's talk about the general form of an exponential. Now, the exponential function would always have a form f of x equals ab to the power x. Now, a shouldn't be 0 because if a is 0, everything is going to go to 0. And x is a real number. Now, b is called the base. Sometimes it's called the common ratio. And x, of course, is the exponent. What about a? A is called the initial value or the starting value or the starting amount. That is a, initial value or starting amount. Now, if b is greater than 1, then the function, the exponential, is increasing or it's a growth function. If b is less than 1, greater than 0, it's a decreasing function or a decay function. All right. So let's look at the first example, problem 2. Now in problem 2, we have f of x equals 3 to the power x. So remember, an exponential always should have this form. So if f of x equals 3 to the power x, then it means that b is 3 and a is going to be 1. There is a hidden 1. It's going to be 1, okay? All right. Now, is this function experiencing growth? Is it a growth function or a decay function? And how do we know that? Remember, we know that by looking at the b. It's right here. Is the b greater than 1? If it's greater than 1, it's a growth function. Yes, b is 3, so it's greater than 1. Since b is equal to 3, or since b is greater than 1, okay? Now, what is the initial value? A is 1, it's hidden. That is 1. But it always should have the form ab to the power x. Okay. Now, because that is the function we have, now when you go to the table, you can fill in your values, right? So if x is -3, you put it in, and then you have your value for y. If x is -2, put that in, 3 to the power -2, which is going to give you 1/3 squared, which is 1/9. Okay, now when x is -1, you have 3 to the power -1, which equals 1/3, which is 1/3. So -1, 1/3. And x is 0, you have 3 of 0 equals 1. So 0, 1. So you keep going like that. When x is 1, you're going to have 3 to the power 1, which is 3. When x is 2, you have 3 to the power 2, which is 9. And x is 3, 3 cubed, which is 27. And that's it, okay? That's it. And then, what about plotting the points for a graph? What about plotting the points for a graph? So you have all your values, right? You have all your values. So you try to draw the graph on that. And with this, you're going to get something like that. Something like that. Okay? Now you can check it out as well. Now let's look at the next thing, the next problem. Now with this one, we have g of x equals 1/2 to the power x. Again, you have g of x, the general form is g of x equals a to the power b. A times bx. So my a again is going to be a 1 here. And then my b is 1/2. Now, going back to what we said up there, if b is less than 1, the function is a decaying function. Now, since b is less than 1, greater than 0. Now, you're going to put the values in. Here you have fractions, so please take your time. Remember the negative exponent rule. That is going to help us. So, you have 1/2 -1. Now, 1/2 to the power -1 is going to be 1/1/2, right? And what is 1 divided by 1/2? It's 1 divided by 1/2. 1 is 1/1, right? So you're going to have 1/1 times 2/1, which gives you 2. So it's kind of like if you have 1 divided by a fraction, you just flip it. Flip the fraction. So you have 2/1, okay? All right. So when x is -1, y is 2/1. Mhm. Now, what about when x is 0? So you have 1/2 to the power 0. Any number to the power 0 is 1. So that is a simpler one. Now, what about 1/2 to the power 1? That is also another simple one. It's going to be the same thing. So 1, then 1/2 or 0.5. Then what about 2? You have 1 over 2 to the power 2, 1 over 4. So you have 2, 1 over 4. That's about it, okay? Mm. And then you draw the graph. Now, because there's a decaying function, but we'll talk about that in a little bit. You're going to have something like that. Mhm. So that's what you're going to have, okay? All right. Given the function f of x equals mx plus b, and there is a linear function, respond to each of the following. Refer back to the previous lessons as needed. So f of x equals mx plus b. What is x? X is the inputs. Remember, this would also be on the final. F of x represents the output. The graph of f is a line with a slope m and vertical intercept b. And this is from lesson 1 and lesson 4. Now, on the grading or on the graphing grid below, draw an increasing linear function. In this case, what can you say about the slope of the line? The slope of the line for an increasing function should be greater than 0. And it should increase from left to right. All right. Now, what about the other way? When it's decreasing, you have that, then you have something like this. Okay, that's a decreasing function. F. The defining characteristic of a linear function is that the average rate of change, also called the slope, is constant. Is constant. The domain of a linear function is all real numbers. Remember, this is not a practical domain, okay? Now, the next example, I'm going to skip it. Please go through it. It's just like what we started with. You have a linear example or a practical problem, and then you have an exponential as well. Okay. And then you have a constant, and you're supposed to choose between them. Okay, I think I have to go through it. So let's do it. So it says on December 31st, around 10 p.m., you are sitting quietly in your house watching the Clark's New Year's Eve special when there is a knock at the door. And who is at the door? It was a man dressed in a three-piece suit and tie. Wow. And holding a briefcase. And you cautiously open the door. Now, this man says he's a lawyer from your deceased great uncle. Now, your uncle left you some money, and it comes with three options. The first one is $1,000 would be deposited on 31st in the bank account, and each additional day you have $1,000 added to it. So $1,000, and then each additional day you have $1,000 added to it. Wow. B says 1 penny would be deposited on December 31st in the account bearing your name. Each day the amount will double until December 31st. And then option C is take $30,000 and go. And I know a lot of us would choose option C because we don't have the patience. We don't have the patience to wait. Now let's see which one is the better option. And of course, that is what you want to find. Which option would give you the most money after 31 days? So January 31st, everything ends. Let's look at them. Now for option A, $1,000 to start and $1,000 a day, this is what you're going to have. So you have 1,000 for the start. After a month, you have 2,000, 3,000, 4,000 for 30 days or 31 days. And at the end, you have 32,000. Now let's go to the next option, B. So with B, you start with a penny and then it doubles to 2 cents, 4 cents, 8 cents, 16 cents, 32 cents, 64 cents, $1.28. And look at what is happening. Wow, 21,474,836 and 48 cents. Wow. And that is why sometimes you have a lot of interest accruing on your loans, because if you leave them uncared for, because it's exponentially set up, it's just going to shoot up like that. Now we are supposed to find the symbolic representation for each situation. Now for A, remember we have $1,000, and every day you have $1,000 being deposited into it. Now for B, you have 1 penny, right? And it doubles. So this is what you do. The 1 penny is the initial value or the starting value. So 0.01 times it doubles, so times 2 to the power t. So we have our A times B to the power x. Now what about C of t? I think that I didn't read that, but that is also there. It says take, oh yeah, I did read it. Yeah, take 30,000 and go. So that is a constant. So it's a constant function. So this is linear. This is expo. And this is linear or constant. Okay. Now what about the graphs? Remember, the constant term is not the difficult one, because that you're going to get a straight line. For B of t, so this is C of t. Now B of t is going to be like that. So this is B of t. And then A of t is going to be A of t. So there's also a straight line. Okay, all right. Now what about the practical domain? The practical domain. For A of t, remember we are looking at time is 31 days. It's going to be the same for all of them. Now for the practical range, for A of t, we started from 1,000. Then we ended at 32,000. For b of t, we started with a penny. Then we ended with 21,474,136.48. And then for the constant, you have c of t equals 30,000. For that, nothing is going to change, right? Because it's constant, so it's not going to change. Now, based on the graphs, which option would you give the most? Would give you the most money after 31 days? Of course, you know that from the table. You know that option B, right? Option B, the exponentially set up one. Okay, all right. Now, as t increases from day 20 to 21, describe how the outputs change for each function. So from 20 to 21, so you're going to have a of 21, okay, 22,000 minus 21,000. And then for b of t, now because it is a doubling thing, to describe how the output change with time, you have to, because it's doubling, right, from top to the bottom, so you have to pick day 21 divided by day 20. So this should give us 167,772 over. So we have 83,886.08, and this should give you 2. So that's the doubling amounts, okay? It should give you 2. So if you doubled something and then you divide both of them, you get 2, right? Because you just doubled it. Now, what about if t increases from day 23 to 24? Again, it's going to be the same thing. So you're going to have 24 from the table. You have 25,000 minus 24,000. For this one, you have b of 24 divided by b of 23. And then when you do the division, you get 2, okay? Okay? Now, generally, you say that a of t increases by 1,000, b of t doubles, right? So that's the next thing. A of t increased by 1,000, b of t doubles. In other words, a of t grows by addition or linearly, and b of t grows by multiplication or exponentially. In other words, a of t grows by addition or linearly, and then b of t grows exponentially or by multiplication. All right. Given the following table, explain why the data can be best modeled by an exponential function, use the idea of common ratio in your response. So how do we work on this? Now, to know if this table is exponential, remember that for exponentials, you are either doubling or tripling or quadrupling or whatever, right? So we have to look out for those clues. We have to look out for those clues. So this is what we are going to do. We are going to pick the change in y. Oh, that is the value, right? That is the value. So the first value, when x is 0, we have y is 15. That is the initial value. That is our a. That is our a. And then our second value is when x is 1, y is 12. Now, these values are these y values is what doubles or triples or whatever. So to make sure that this table is exponential, now you're going to divide 12 by 15. And when you divide 12 by 15, what do you have? I think you have 0.8. And then you're going to check for that too. So you're going to do 9.6 divided by 12. What is that? Is it 0.8? Yes, it's 0.8. Then you're going to go to 7.68 divided by 9.6. That gives you 0.8. 6.14, oops, over 7.68. Put it in a calculator, you get 0.8. What is going on? It means 0.8 is going to be our B. Is going to be our B, which is our base, okay? It's going to be our base, or our common ratio. So this tells us that this is exponential. All right? Okay. Now let's look at question B. Question B. Determine an exponential model f of x equals ab to the x that fits these data. Okay. How do we do that? Now we know that we've got 0.8, and that is going to be our b, right, for our exponential function. Now, what is a? A is 15, the initial value, right, when x is 0. So we have f of x equals a is 15 times 0.8 all to the power x. Remember, you don't change the exponent, sorry, to the power x. And that's it, you're done. Okay, you're done. Now, what about c? For c, it says find f of 10. So you have your exponential. So you put that in 15, 0.8 to the power 10. And that should give you 1.61. 1.61. Now, what about D? D says determine f of 50. Again, you do the same thing. F of 50 will be equal to 15 times 0.8 to the power x of 50. And that should give you 0.000214. That's what you should get, okay? All right. Now let's get to another important part of our lesson, that is the characteristics of exponential function. We already know the form of exponential functions. X is going to be our input. F of x is our output. We should already know that. Now, the graph of an exponential is always going to have a J form. always. So if you've seen that previously from what we've done, we are always getting something like a j, is because it's an exponential function. Okay. Now the vertical intercept is always going to be 0 for x, and then a, our initial value. Okay, 0 and then our initial value. So our initial value is our vertical intercept. Why? Because x is 0. X is 0. B is the base or common ratio, right? Then another way to find the vertical intercept, of course, x is 0, so you put it in. I mean, we know that. We know that already. Now, let's look at these situations. When the graph is an increasing graph, remember we talked about increasing or decreasing graph previously, I think in lesson 1 or 4. Now, you are reading it from left to right. So if it's increasing, or if the y values is increasing from left to right, you say that the function is increasing. Now, how do we know that an exponential function is increasing? B should be greater than 1. Okay, B should be greater than 1. Now, the domain is all real numbers. And then our range is going to be f of x or y is greater than 0. That is 0 to infinity. It's greater than 0. Remember, it's not greater or less, right? It's just greater. So you have parentheses for both sides. Now, what is the horizontal intercept? It's none. The vertical intercept, we already talked about it. Now, the horizontal asymptote, and we know what that is, right? The horizontal asymptote is always y equals 0. And then it's increasing. Now, what about a decreasing exponential? Now, the domain is the same. The range is the same. Horizontal intercept is the same. Vertical intercept, same. Horizontal asymptote, same. Wow. And the function is decreasing. Now, let's look at this problem real quick. Now, this is a media lesson, so I'm going to skip this one. So please try and then do it by yourself. And now we're going to look at these ones. Now, when you go to the calculator, if you're supposed to draw this, now here you have the window. I'm going to go to the calculator real quick and then draw this first one, 335, 1.25 to the power x. I'm going to share my screen. The 335 and then times 1.25, so 1.25 to the power x. And this part, you don't want to worry about this part for now. Now, if you go to graph, oh yeah, I think my window is a mess. I'm going to do a standard window, or probably check what the window should be. I think, yeah, it's going to have a problem. Now, the question gives us the window, so it says, okay, x is negative 10 to 10, y is 0 to 1000. That's why. So y is going to be 0 to 1000. So I'm going to go back. Zero to 1000. Okay, so this is better. Remember, the horizontal asymptote is always y equals 0, which is the x-axis, All right. Now, let's go look at the rest of the questions. Now it asks us, what is the initial value? The initial value is A. A. Now remember, you have to draw the graph in this box. So the initial value is A, 335. The base is 1.25. What is the domain? All real numbers. Okay, all real numbers. And then what is the range going to be? So the range is going to be f of x is greater than 0. Now what about the horizontal intercept? None. Vertical intercept is 0a, or the initial value, which is 335. The horizontal asymptote is always y equals 0. Is the function decreasing or increasing? The function is increasing. Increasing, and then you put that there. Now let's look at this one as well. I'm going to go to the top. So from this one, clearly you will see that you have a decreasing function. Why? Because b is 0.75, which is less than 1. So again, you draw your graph, and you're going to have something like that. And this is a decreasing function. Now, what is the initial value? 120, which is A. What is the base? 0.75. 0.75 for the base. What is the domain? All real numbers. What is the range? F of x is greater than 0. Okay. Oh, g of x, sorry. It's g of x. G of x. And then what else? G of x is greater than 0. What is the horizontal intercept? Is none. Vertical intercept is 0. 120. Y equals 0. It's decreasing. Decreasing. That's it. Now, what about 9.3? Now, in 9.3, we want to solve exponential equations graphically and algebraically. Graphically and algebraically. Now, let's look at some examples that would help us. Again, we're going to still use the intersection method, so hopefully you remember that. Now, there are some guidelines that you should remember. I'm going to be talking about some of them as I go through the problems, but please read through the guidelines. It's going to help you. Now, the first one is a media example, so I'm not going to worry about that one. My hope is that you watch the video. So let's look at this problem. In each situation below, you will need to graph to find the solution to the equation using the intersection method described in this lesson. Okay. So again, I have my y1, y2. The window is going to be big, especially for y. So let's go to the calculator. So you go to y equals, you're going to erase. Now, y1 is 54 times 1.05 to the power x. So 54 to the power x. And And then my y2 is going to be 250. $250. And then for your window, now for right now, look at my y2 is 250. So you know you're getting something very big. So I might as well, I'm just going to keep the x as it is. I might make changes later. I'm going to do 500 for this. So let's go check out the graph. It doesn't look good. So I'm just going to change, my x should change, especially the positive, let's see. Yeah, especially the positive side. So I'm going to go back and then do, let's say 50. And then I'm also going to decrease my y to 300. Oh, this is better. This is better. This is better. So now to solve this, I'm going to solve for x. I'm going to do second trace, 5, enter, enter, enter. Oh, wow, my x is 31.4095. But if you want to do two decimal places, 31.41. 31.41. So I have that. Okay, so that is my solution. And then you write your window and then draw a very nice graph. Okay, it's a sketch, but it should be nice. Okay, so let's go back to all right. Now what about B? What about B? Again, same idea applies. Same idea applies. Now, if you look at B, look at our A here. It's 2,340. Y2 here is 1,250. So these are going to be very big values. So if you want to go back to the calculator, remember Y1, Y2. So if you go to the calculator, you are going to have, so all I'm doing here is using the graph to solve for x. So I go to y equals, I'm going to erase this, and then I'm going to go 2340, and then parentheses 0.82 to the power x. Then I come down here and I'm going to do 1250. Now I go to window. I'm just going to keep, for the x is going to stay this way. Then I'll check what is happening. Here I'm going to do 0 to 2500 just to stay safe. Okay. It is not that bad, but I could have done better on it if I increased the positive y again to 50 here, and then also increased this to 3000. Okay, this is better. Okay, this is better. Now to find my x, second trace, 5, enter, enter, enter. 3.16. Wow, 3.16. And then I draw my graph, okay? And then put your window there. So really, if you look at so far, if you look at lesson 9, yes, it does need practicing, but it's better than some of the sections we've looked at previously, right? So I'm going to leave C to you to finish it. And then now I'm going to be talking about how to calculate exponential equations algebraically. But before that, we want to talk about exponents again. We did talk about exponents a while ago in lesson 7. We're going to do that again, but this time around in a different way. Now, if I have, look at the top here, b to the power x equals b to the power y. bb at the bottom for the bases, then x equals y. I think this makes sense, right? Then x equals y. We're going to use this understanding to do a lot. We're going to use this understanding to do a lot. So look at this first one. You have 4 to the power 2x minus 1. Now, because you have 4, now you always want to think about the number that is not an exponent. Can I change it to have an exponent? Yes. 64 is 4 to the power 3. And you always want to make sure to set it up as the other one, the base is set up. So 4 and then 4. So you have 2x minus 1 equals 3. 2x equals 4. Divide by 2. You divide by 2. X equals 2. Wow. X equals 2. Okay. And then you're supposed to draw this on a calculator, or get it on a calculator and draw the graph. So let's go to the calculator again. Y equals, so y1, y2, so I'm going to clear this. So I have 4 to the power 2x. Now you have to make sure that everything is going to be, the exponent, you watch out for the exponent. Yes, 2x minus 1 is all exponents, right? You don't want the 1 to come down. And then my y2 is going to be 64. Now I'm going to go change the window and make this 100. And then I'm changing x to a 10. Oops. Look at what I have. I might as well decrease the y positive. Maybe 2. Okay, that didn't help, obviously. So this, I think, is better. Okay. Then again, you could solve for x, right, by doing second trace, but you already did. Now, we did, and then we got 2. Now, you always want to check your answer, right? You want to check if it's right. So I'm going to go back. So I have my graph. I'm going to go back and then check. I got 2 for that. So I'm going to put 4. 2 times 2. Remember that is x minus 1 equals 64. Now, on top, you have 2 times 2 is 4 minus 1. 4 to the power 3 equals 64. Is that right? Yes, I checked, and that is right. Now, same idea with this guy. You have 4x minus 4 equals 16. Now, I know that 16 is 4 squared, so I do the same thing. So I'm going to have x minus 4 equals 2 plus 4 and plus 4, x equals 6. I want to check to make sure. So if I check, I'm going to have 6 minus 4 equals 16. 4 squared equals 16. Wow, that is correct. That is correct. Another one is 2x minus 9 equals 27. Now 27 is 3 to the power 3. So 2x minus 9 equals that, plus 9 plus 9. 2x equals 12. Divide by 2, you divide by 2, x equals 6. And then you check. And I think I just checked in my mind or in my head, but you want to check, take your time, and then, yeah, it doesn't take that long, right? So now what about the last section here? So I told you that chapter 9 and 10, or lessons 9 and 10, are not a lot. What about this part? So again, just as we've looked at applications of several functions, we want to do the same thing here. Now, this first one is a media example, so please go back and watch the video. But I want to start by looking at this one. Again, this is an application problem. Okay, in 2010, the population of Gilbert, Arizona was about 208,000. By 2011, the population had grown to 215,000. Assuming that the growth is exponential, it says there is a growth, so you know it's an increasing function. Assuming the growth is exponential, construct an exponential model that expresses the population P of Gilbert AZ X years since 2010. It says your answer should be written in function notation. 3 decimal places is fine. Okay. So let's see what we have. Remember that from the top, our starting time is 2010, right? And the population was 208,000. So this becomes our initial value, A, right? Now what about our B? What about our B? How do we even get our B? Now, remember from the previous problems when we had a table, we pick two y values, divide them, and then we get our B if it's doubling or whatever. So we're going to do the same thing here. We have 2010, we have 2011, yeah. So in 2011, we had 21500, and then 2010, we had 208000. So what would this give us? It's going to give us approximately 1.04. Remember, 3 decimal places. That's what the question says. So we have our B here. So that's it. So P of X, because we are using P, that's what the question says. Our initial value is 208,000 times 1.0 to the power X. Or you could do T, right? T. I'm using X for that. And that's it. That's all you do. That's all you do. Now you go to B. Use this model to predict the population of Gilbert, Arizona in 2014. Write your answer in a complete sentence. Okay, let's do that. So we have our model. So in 2014, now this is it. In 2010, that is our starting point. So T, our time was 0. In 2014, if in 2010 our time was 0, it's kind of like someone is born in 2010, right? So if you are born in 2010, you are 0 year old or you are 0 years old or whatever. So in 2014, how old will this person be? 4 years. So you use 4. Don't use the 2014. So T is 4. So P or X is 4. Or 4 equals 208,000, 1.034 to the power, 4. and then put this in a calculator. And then what are you going to get? I think you're going to get 23776.67, and approximately we can say 23776.63. Okay, so that would be the population in 2014. Now, because we are talking about population, we ignore the 0.67, right? Because we are talking about human beings, so it's better to be less than rounding up. So now, what about C? In C, we had, according to this model, in what year will the population of Gilbert, Arizona reach 300,000 using the calculator? So here we are looking at our Y, or our population, reaching 300,000. So you're going to have 300,000 equals 208,000, 1.034. So if you go to the calculator, you have Y2 or Y1, Y2, Y1. And then remember, this is going to be big values, but let's try it. I'm going to try it with you. Two zero eight. Oops. 208. 1.034 to the power x, and then here I have 300,000. So these are very big numbers. 300,000, very big numbers, right? So setting up my window, my y should be very big, very big. Now for my x, I'm just going to leave it as it is. If I go to my y, I'm just going to do 320,000. And then go to graph. Okay. So it's still not the best, so I'm going to change this to the y value, and then the x, I'm going to change that a little bit to 350,000. And then for x, I'm going to do the positive x to be 20. Okay, this is better, right? This is better. So second, trace, 5, enter, enter, enter. Oh yeah, 10.95. 10.95 for x. That's what I have. So it means that the question says, in what year will the population reach 300,000? Now my t is 10.95. So I'm going to, let's go back. Okay. And t, remember I had something like that. Right? And this was 10.95. 300,000. So t is going to be 10.95, which will give me a 10. Yes, because it's not up to 11 yet. You don't want to do 11, because if you do 11, it's going to be more than 3,000, right? I mean 300,000. So now let's start. So 2010, and then after 10 years, you are in 2020, right? 2020. So that's it. for that. Okay. Now, let's look at the next question. 1 8-ounce cup of coffee contains about 100 mg of caffeine. Now, here you are given the function, right? A of x equals 100 times 0.88x. It gives you the amount of caffeine remaining in the body. Okay, x hours after drinking a cup of coffee. Okay. It says answer the incomplete sentences. All right. Identify the vertical intercept. That's the first thing. Now you know the vertical intercept is always 0, a, which is the initial value. And what is a? 100. So 0, 100. So what do you say in a sentence? The 8-ounce cup of coffee contains about 100 mg of caffeine. So when you drink it, there is 100 mg of caffeine in your body. And that's it, okay? What about B? How much caffeine remains in the body 8 hours after drinking a cup of coffee? 8 hours. So what do? You put 8 into the function. What does that give us? It's going to give us 35.96. So what are we going to say about this? We're going to say that after 8 hours of drinking a cup of coffee, about 35.96 mg of caffeine remains in your body. 35.96. What about C? Okay, C says, how long will it take the body to metabolize half of the caffeine from 1 cup of coffee? So here we are looking at 1 cup, right? 1 cup of coffee, right? And we are looking at a metabolism of half of the caffeine, right? Okay. So we are looking at 1 cup. So how long we are looking at? How long will it take? 50 mg, right? 50 mg. So that's a half of caffeine remaining in the body. Okay. It says use the calculator to solve that. So we're going to get 100 0.88 to the power x equals 50 mg. Okay. Where are we getting the 50 from? It's 1/2 of 100, right? Or 100 mg. 50 mg. So put this in the calculator, you should get x equals 5.42 days when you do this in on the calculator. Now let's look at problem 24. Oh, let's look at D first. D for this problem. And then, according to this model, how long will it take for all of the caffeine to leave the body? So the caffeine will continue to decrease, and over time approach, but not equal 0. Okay, so continue to decrease and over time approach, but not equal 0. Problem 24. Now here we have a certain bank compounds interest on the balances annually in all savings accounts. The function they use to compute the balance is f of t equals p in parentheses 1 plus r close to the power t. Now P is the principal. So now we are going to a bank. T is the time in years. R is the annual percentage rate. If a savings account has a balance of 5,000 at a 3% annual interest rate, use the function to find the account balance after 4 years. So that one, remember you already have the function. So if you want to find the account balance, then you have f of 4 equals P, right? And what is P? 5,000. So you do 5,000. That is from here, times 1 plus R, which is what? 3%. So 3% is 0.03 to the power 4. This should give us 5,627.54. What about the amount of interest after 4 years? The amount of interest after 4 years. So we know the amount after 4 years. So you subtract, right? 5,627.54 minus 5,000. Okay, minus 5,000. What do you get? 627.54. So the interest earned after 4 years is that. Now use the TI-84, using the TI-84 calculator, after what time, T in years, will the account have $11,400? $11,400. So how do you set this up? 5,000, 1.03 C equals 11,400. Put this in the calculator, and then your T will be 27.88 years. Okay, put that in the calculator, and that's what you're going to get. And then draw the graph. Draw the graph. So this is where I'm going to end this video. So please try to keep practicing. Go into the lessons, and then watch those videos as well. Thank you.